So now we're ready to move on to a different type of calorimetry problem. And in this case, we're going to look at one that's very close to what you'll be doing in lab this week. So I hope it'll set the stage for you to successfully complete your calculations in lab and understand what's happening there. In the last example, we saw a warm or a hot material releasing energy as it cooled. That energy was absorbed by the water that surrounded it. That's why the water's temperature came up from 22 to 25. But another way that energy, or another place that energy could have come from for the water to gain, is through a chemical reaction that might occur in an aqueous setting, so in a water setting. And so that's what I've set up here. And I apologize if I've already got it written down. I figure you could pause and write down the example if I'm going a little bit faster than you're able to keep up during the video today. So let's suppose that we added 0.21 moles of a chemical X, and it reacts in a calorimeter. That's important again, it's insulated. That contains 200 grams of water that's initially at 21.8 degrees Celsius. The reaction has an enthalpy change of negative 31.6 kilojoules per mole. That means it's going to release energy, right? All the heat released by the reaction is absorbed by the water. So what's going to be the final temperature of the water? We know it's going to rise from the 21.8. Let's figure out what the final temperature of that water would be. So here again, we have two things together. Instead of saying a system this time, though, we might say that the energy change of the reaction is equal and opposite to the energy change of its surroundings. Just like I started the last example, but replacing the generic system with a reaction now. Again, only heat is involved, so Q of the reaction equals negative Q of the surroundings. The water is the surroundings. It's going to undergo a temperature change. We're kind of hinted at that here. So for the water side, it's going to be M CSP delta T once again. But the reaction is something that occurs technically at a constant temperature, and reaction heats are quantified by N times delta H of the reaction. All right. So the energy that's released, in this case by the reaction, is absorbed by the water. Now in lab, I'm going to go a slightly different direction right now than where you'll be going in lab, but to give you that heads up, in lab, you'll be trying to solve for this delta H, okay? Today, right now, we know the delta H of the reaction, and we're trying to solve for something over here on the water side. But just as a heads up, in lab you'll be setting up essentially this same equation, but instead solving for the enthalpy change of the reaction. All right. Now, this time I'll go ahead and plug in some of the numbers and go right to the numbers. So we know we had 0.21 moles, 0.210 moles of the X times negative, now I'm going to convert 31,600 joules per mole. I multiplied the 31.6 kilojoules by 1,000, which is what a kilo represents, because my heat capacity on the water side is in joules. And so I have to have that energetic matching between their units, right? Joules and joules, otherwise our scales are off. So we had 200 grams of water, the usual 4.184 joules per gram degree Celsius, and now you can see the joule parts are going to cancel out. And then temperature change. I don't know the final temperature. That's what I'm after here. So I'm going to put in a variable to represent that, TF minus the initial 21.8 degrees Celsius. So I have a little bit of algebra to do here. On the left side, I get, when I multiply these two out, negative 6,636 joules. The per mole part has canceled, technically. On the right side, the 200 and the 4.184 give me a negative 836.8. And then this needs to be distributed, right, this joint product to both numbers in the parentheses. Essentially what I'm doing now is like taking 5 times x minus 3. You have to take that 5 times both the x and the 3. So this would be negative 836.8 times TF plus then, because the negative times the negative, 18,242.24. So we do a little bit of algebra. I'll subtract this over to the left side, and I get negative 24,878.24 equals the negative 836.8 TF. Divide by the negative 838.6. My final temperature is 29.7 degrees Celsius. Now you want to always check your answer mentally to see if it makes sense. Does it? We started with some cool water and we conducted a reaction that released heat. That heat goes into the water, which should raise its temperature, and 29.7 is higher than the 21.8. All right, so that's a little bit of a check that you can have, and it's always good to think about that, be a little bit critical of your answer before you just move on to the next one. Right? So between the previous one and this one, you've seen some good calorimetry examples. There's a little bit of variation on it, but usually you're starting with the first law for how your system is reconstructed, how your universe is rebuilt, what's your system, what's your surroundings, and then you have to figure out which style of heat you have for each of the two sides. Okay? So in the next segment, we'll move on to how do we calculate delta H's, how do we calculate heat changes for reactions that we can't conduct in a calorimeter. So I'll be right back in the next segment for that.